Today I've got one more mixing problem for you, this time with different fluid rates coming in and going out. We've got a 500-gallon capacity tank that has 100 pounds of salt in it initially that are mixed into 200 gallons of water. So that's our initial condition. Coming into the tank, we have salt water with a concentration of 1 pound per gallon, and that's pouring into the tank at a rate of 3 gallons per minute. Moving out of the tank, we've got well-mixed salt water, but it's only flowing out at 2 gallons per minute. So this tank is not losing as much fluid as it's gaining, so it's going to be increasing in volume, I guess up to that capacity of 500. So our goal is to write and sketch a function that models how much salt is in the tank, we'll call it y, as a mass, right? So in pounds, as a function of time in minutes. And then we'll also take a look at the concentration function related to that and analyze the end behavior of that function. First, to set up our differential equation, remember we'll set up dy dt, the rate of change of salt in the tank as a function of time. We'll set it up as a difference, rate in minus rate out. Remember, we're talking about rates of salt per gallon coming in and going out. So the initial condition that we've got, just to include everything here, is y of 0 equals 200. When time is 0, we have 100 pounds. So as far as the rate in, that's pretty easy. It's a constant amount because we know the concentration in is a constant 1 pound per gallon. And we know that 3 gallons per minute is the fluid rate coming in. And so multiplying those fractions together, we've got 3 pounds per minute. Now, for the rate out, we're going to need to think about the concentration again a little bit more. So remember, concentration is the same as mass divided by volume, or in this case, weight divided by volume. So our mass or our weight at time t is going to be y pounds. And the difference in the flow rates, if we think about just the liquids, we're gaining 3 gallons per minute and we're draining out 2 gallons per minute. So that is a difference of positive 1 gallon per minute. So that means each minute this tank is increasing in volume by 1 gallon. So what that means is we can set up a linear expression to describe the volume of the tank, or the volume of water in the tank at time t. And that would just be your intercept, 200, plus the slope of 1. That would be a coefficient here. If it's anything other than 1, you'll see it written there. 200 plus t in this case. So that's every minute we're increasing the volume by 1. So now we're ready to set up that rate out. The salt rate out, then, we would take 2 gallons per minute, which is the fluid rate out, and multiply by that variable concentration. Remember, our mass or our weight is y as a function of time, so we'll write that as our numerator. And then in the denominator, we insert that volume function that we talked about. And that will be a good fraction to describe at time t the concentration of the salt in the tank. So we'll multiply that concentration by the fluid rate, and that gives us 2y divided by 200 plus t gallons per minute. Actually, that's a typo. That should say pounds per minute there, because that is a solid amount. That's your pounds per minute. That's your dy dt equivalent. So our differential equation that we need to solve then would look like 3 minus 2y over 200 plus t. And again, with the initial condition of y of 0 equals 100. Now the problem is, to solve this one, we can't just use a separable strategy, because this one is not separable. We've got a y and a t in there. What we can do, though, instead is set it up as a linear differential equation and use that integrating factor method. So put it in linear form first, right? We'll keep dy dt on its own side. We'll move that y linear term to the left side and leave the 3 on the right. So we're adding it over, and I rewrote it a bit, taking the y out for the end, so we can see it in that standard form, where this 2 over 200 plus t becomes the p of t function. That's the function we'll put into our integrating factor formula. Remember, to get that mu of t, we'll integrate and we'll raise that to the power of e. So we'll say e to the power of the integral of 2 over 200 plus t dt. When we do that, the integral becomes a log function. And so we have e to the power of, I'll take out the coefficient of 2, times the natural log of 200 plus t. And that is in absolute values, but that'll go away because we can use log properties to take that coefficient of 2 and write it as an exponent of the logarithm. So we can rewrite this as the log of 200 plus t squared. And since we're squaring those numbers, we don't need the absolute value anymore. So undoing those inverses, e to the log, those are inverse functions. They'll remove each other. We'll be left with just simply 200 plus t squared for our mu of t function. So remember, for that integrating factor method, we need to take that expression and multiply it by each term of the differential equation. And so that looks like 200 plus t squared times dy dt, and then we multiply it by those other two terms as well. Don't forget the right side also. This middle term simplifies kind of nicely. We can divide one of those 200 plus t factors out. And notice you should see on the left side then something that looks like, as usual, the result of a product rule. We've got a function and a derivative times the derivative multiplied by the other original function. And so I'll rewrite that in that derivative notation, right? This is the same thing as the derivative of y times 200 plus t squared. Double check that. You can use the product rule on that, and you should be able to see exactly those two terms. So now we're ready to integrate. So we'll integrate both sides with respect to t. And on the right, that's just a regular old integral. That one is not too bad. You'll have to use the power rule there along with a little u substitution. On the left side, this is pretty easy, right? Remember, those integral and derivatives will undo each other as well, since we're doing that with respect to the same variable. So all that's left is the inner part, 200 plus t squared times y. On the right, remember, we're using a u substitution here, but du is 1, so there's not a whole lot to worry about there. With the power rule, that goes to 200 plus t to the third power, and the division by 3 cancels with that coefficient of 3. Don't forget, we do need to add a constant c at this point on one of the two sides. So solving for y is pretty easy. Just divide both sides by that integrating factor. And we end up with, on the right, our y equals 200 plus t plus that constant c divided by 200 plus t squared. If you wanted to, you could combine those two fractions with a common denominator to make a rational function, but this is fine too. So all we need to do then is finish out our particular solution instead of just a general solution by plugging in that initial value. So we'll substitute in 0 for t, and we'll substitute in 100 for y, and that will help us solve for that constant c. Doing so, we've got a bit of algebra to do. We can multiply both sides by 200 squared. We can make that calculation. C is going to be a pretty big number, 100 times 200 squared minus 200 times 200 squared. That works out to negative 4 million. So we'll go ahead and replace that in with our C value in our solution, and our particular solution becomes 200 plus t minus 4 million over 200 plus t squared. Don't worry about having to sketch that, but use technology to look at a graph, right? It looks something like this. We've got, as we mentioned, a rational function, and that intercept is where you'd expect at a height of 100. Interestingly, we've got a slant asymptote here. If you were to multiply that all out, you'll see it. You could turn this into a rational function, then do that long division to look for where that slant asymptote would be. But a more interesting way to assess this is to think about the concentration function. We'll get at that same kind of information another way. So let's take a look at that. If we were to take that particular solution and write the concentration function, remember that concentration is the same as mass divided by volume. So also remember that we calculated the volume at time t as 200 plus t. So all we need to do to write a concentration function is to take this mass or weight function and divide it by 200 plus t. And so that looks pretty neat, right? On the first term there, we get just a 1 left over when we divide. For the next term, we'll just increase the power in the denominator by 1. So this concentration function does represent the correct concentration of salt in the tank as a function of time. just as a kind of double check, remember at time 0, that should be 100 pounds per the 200 gallons that we started with. And that does work out correctly if you try to compute that. A graph of this one is pretty revealing. I changed the scale a little bit because concentrations obviously are much smaller than the actual weights. But notice we've got that initial condition that we expected, a height of 0.5 at time 0. And notice that concentration is increasing, but the end behavior is a little bit easier to identify here. Right? It's not going off to infinity at a certain pattern, it's actually leveling off at a concentration of 1. We can see that numerically also by calculating the limit as n approaches infinity. I guess actually another typo, this should say t, right? As t approaches infinity, we end up with a concentration approaching 1 pound per gallon. That makes sense, I think, right? Because eventually if we keep pouring fluid into the tank, we should be approaching the concentration of the fluid coming in.